Hey guys, welcome to day 9 solving exponential functions. Okay, we're going to go ahead and have two sections of this. We're going to have some methods to introduce for the first video, and then we will have a lot of practice for the second video. Okay, so let's go ahead and begin. Method 1 is called the same base method. Okay, and primarily this is done when you don't have a calculator. Okay, so we know the situation of what it is now that you could have a calculator at home. However, in college or on like the SAT non-calculator portion, you'll have to know how to do these skills. So very, very important that you still concentrate on learning how to do these, even though you could get away with using a calculator right now. Okay, so the same base is we're going to identify these two bases, which is 27 and 81, and we're going to see, do they have some kind of factor in common? Okay, so 27 is divisible by 3, and so is 81. So they do have a factor in common, which is 3. Okay, so we're going to change this 27 to 3 cubed, because that's 27. And we're going to change 81 to 3 to the 4th. Okay, because 3 to the 4th is 81. Now we still have this power of 3x, and these are still equal to, but the reason why I did that is so that we could get the same base. Okay, so you have a 3 and you have a 3. So we're almost there. So we have powers raised to a power. So when we were looking at units before, if we had something like x squared that was cubed, we knew that we would multiply the powers, because a power raised to a power, you multiply, and it would be 2 times 3, okay, which would give me x to the 6th. Now this is different from, just quick review, x squared and x cubed. When they're multiplied, we add their powers to get x to the 5th. Okay, so when you have two bases that are multiplied, just a reminder, we add. But if we have one base that has two powers, a power raised to a power, we are going to then multiply. And that's what we're trying to do here. We're trying to see 3 is the power, but then it's further raised to the power of 3x. So if I multiply that, I'm going to get 9x as the power. And yes, these bases are still 3. So it'll be 3 to the power of 9x is equal to 3 to the power of 4. Okay, and this is what we wanted. We wanted the same base. Because when the bases become the same, then it becomes negligible. We don't even have to look at the bases per se anymore. It's all focusing on, since I'm solving for x, it's focusing on now of, all right, so if the bases are the same, well, then I can do the following. I can basically negate them to where I don't have to look at them. And what I'm really setting equal to each other is then the powers. Okay, same base, then the powers are the only things that remain. So this 9x and this 4, simply I'm going to use like Algebra 1 skills and just divide both sides by 9, and I get 4 ninths. Okay, so 4 ninths is x for this method. Okay, so you would see something like solve for x on this, or solve the equation, and this would be your answer. Okay, just want to make sure that you understand once more that these are primarily for the non-calculator portions of tests. Okay, all right, so let's go ahead and move on to method 2. Method 2 is going to be using logarithms. Okay, so logarithms. And what we're trying to do is we're trying to solve it by rewriting it to where it becomes a log of some kind. Okay, and this one we have to use a calculator. So the one before was a non-calculator. This one will be with a calculator, if you will. Okay, so here's what we're going to do. First of all, I need to recognize what pieces I have. I have a base raised to a power is equal to like a number. Okay, notice that these two pieces are on ground level. They're on the same level, if you will, and that the power is up here all by itself. Okay, so identifying what you have is a big start of how to use logarithms on this question here. Okay, because let me show you something real quick. Let's say that I had square root of x minus 3 is equal to 5. And I asked you to solve for x. Well, you would see that the biggest overarching piece here is the square root. And to cancel it, you would do the opposite. You would do the inverse. You would raise it to the power of 2 on both sides so that this 2 and this square root cancel with each other. And then this 5 squared would become 25. So then whenever you add, you would get 28. So that one's pretty easy to see because all we did is we canceled that square root piece. Okay. So when we have this base raised to a power, our goal with logarithms is to cancel the base, if you will. Okay. We're trying to get rid of this 5. And the way we get rid of the 5 is we're going to apply log base 5 to both sides. Okay, so let me rewrite this just real quick. We have 5 to the 2x is equal to, and I'm leaving room for a reason. We're going to apply a log base 5, here we go, log base 5 to this piece, or that argument, and also to this number here. Okay, so if you will, the ground level is still going to be right here. It's log 5x, or log of 5 to the 2x, and log of 130. The sub-level, if you will, is the subscript of 5. I just want to let you know and let you see what levels these are on, okay? Because what happens here is when you're using logarithms, if you apply a log base 5 to something that already had a base of 5, what happens is these cancel. Okay, they cancel and the 2x is remaining down here. Okay, and then on the right, you just still have log base 5 of 130. And you see now I can plug this into my calculator and then divide by 2 and I have x. Okay, so let me go ahead and finish this off, and then I'm going to show you a little bit of what else happened as far as how did this 2x just come down on ground level, if you will, to match this log base 5 of 130. Okay, so let's go to the calculator real quick, and we're going to go to log base 5, and it's of 130. And if I divide this by 2, so first of all, it's going to be some ugly decimal. Then when I then divide it by 2, I'm going to get this as an answer. Okay, and just a rule of thumb on questions like this that you get decimals, unless it specifies specifically what to round it to, we're going to do a default of 3 decimal places. So log base 5 of 130 is divided by 2. And the way we show the approximate answer is approximately, okay, it's approximately 1.512. And again, a good default is 3 decimal places unless otherwise specified. So you notice we did need a calculator here, otherwise we would not have been able to do this. Okay, so going back to this power of 2x, how did it just come down here to be on ground level? Well, if you remember one of the laws of exponents, or sorry, laws of logs, is that when I have something that looks like this, like 3 log of x, and it was 3 times the log of x. One of our rules that we've learned recently is that we can move this 3 to become a power inside the argument. So this is the same as if you were to write log of x cubed. Okay? Remember, these are interchangeable. They can go back and forth as far as the coefficient or as the power. So over here, when we had log base 5 of 5 to the 2x, what we could have done is we could have written this power, just like I showed you here. We could have moved the 2x so that it was in front of this log base 5 of 5. So 2x times the log base 5 of 5. And that's equal to what it has on the other side, log base 5 of 130. And just like it canceled right here, let me show you right here, it can also cancel this to 1. So if you have log base some number, and the argument is the same number, this is the same as 1. And just so that you can see why, is that if we were to take log base 5 of 5, again, and we said we don't know what it equals, but I know that if I rewrote this with the reverse Hart method of 5 to the power of question mark equals 5, what question mark would equal in order to make this true would have to be 1. So if question mark is 1, then all of this is 1. Okay, so that's how this becomes 1, so that you're left with 2x equals what you got on the right side. Okay, so that cancellation of 1 can happen there, or if you see it earlier, a lot of people struggle to see it here as easily, that 2 will cancel to a form of 1. And yes, this 2 basically just comes down and meets on ground level with log of 130, log base 5 of 130. All right, so let's keep going. Method 3. Method 3 is going to talk about graphing. And method 4 is going to be talking about a table. So like using the table. So if I wanted to graph these, I have two functions. I have a function on the left side of this equal sign, and I have a function on the right side of this equal sign. And if I want to find x of what it equals, this is our third method that we can do. We're going to graph each one. We're going to graph this one as our first function, okay? So we could say y sub 1 or even f of 1 of x. And our second function is going to be f of 2 of x. And the way that I'm showing you with this primarily deals with the notation in the Inspire. Okay, so let's go to the graph. On the first one, we're going to put 4 raised to the power of 3x. And then it graphs. Then we'll press tab to get our second function, and you see right there f of 2 or f2 of x. We're going to say is the right side of the equation is equal to 6,000. So I did the left and the right. Now you don't see 6,000. I mean, the highest you almost see is 7. So we want to see where it would show up. We want to have a big, huge kind of like an overview picture of these graphs and where they could possibly intersect. So let's go to Window. We're going to go to Fit. And now you see there's a function here and there's a function there. And somewhere in between is where they kind of intersect. So if you need to zoom in from here, then we can go Menu, Zoom in. And let's say we want to zoom in somewhere around here. Okay. And you see real quick that these numbers are so big that it's hard to even see the intersection. So the graphing method can be a little bit difficult at times depending on what this zoom fit shows. Okay, so let's zoom out just a little bit. And then we will see that our goal is to find the intersection between these two graphs. Okay, so you see that it can get a little bit dicey and a little bit difficult to see. So let's kind of reset in case this happens to you. Let's go to Window, let's go to Fit, and now let's see if we can find, I'm going to move these equations just out of the way, and let's see if we can find where the intersection would lie as far as between 6,000 and this 4 to the 3 of x, okay? Or 4 to the power of 3x. Okay, so let's go ahead and go to Menu. We're going to go to Analyze Graph, and we're going to look for the intersection. We're going to look for the intersection between both of these graphs, okay? So again, because this is difficult to see, I'm going to kind of go big as far as maybe it's all the way here to the left and then all the way to the right. And you see no intersection popped up, okay? So what we could do is we can assume that it's going to be further to the left. So I'm going to zoom kind of out just a little bit, way over here, okay? And it could possibly, remember, a big pivotal point of our graphs, okay? Let me go to the graph again. A big pivot point with exponential graphs, and I'm primarily talking about this right here, tends to be when x is 0, like the y-intercept, if you will. And if x is 0, then this is going to be at 0, 1, okay? That's our key point. We've talked about this in previous days of this unit. So our key point of when it crosses the y-axis is going to be 0, 1. And then if I were to draw it, it looks something like this is what the exponential one. And then I have this one that's at 6,000, way up here at 6,000. And then it's going to intersect somewhere here. And this was just a rough sketch. So if I wanted to see, by using this graphing calculator, a good window of lower bound to upper bound, chances are is what I'm looking for is just to the left of the y-axis and anything to the right. It should catch, like in between here, it should catch that intersection. And I just wanted to show you as far as what you can do knowing the key point of the default exponential function. Okay, so let's come back over here. So knowing that, we're going to say, let's try again with the analyzed graph. We're going to go for the intersection. And now we're just to the left of the y-axis. And then to the right, we'll just keep going until we see this intersection pop up. And we see this intersection pop up when x is 2.092. Okay? So for this one, x is going to be approximately 2.092. So manipulating the window, and yes, there's other ways that you could have done this. You could have come over here to this graph, and you could have said, well, let's look at this window, and let's change the settings to this window. And if the maximum was at 6,000, we could put, well, what if we put 6,500? And we could put 0 as the y minimum. So when I graphed it, it looks a little bit more easy to see as far as it looks picture friendly, if you will, like this one did, the way we sketched it. But you might struggle as far as to see that this down here is the x-axis and this is the y-axis. So this is just another way that you can see when would that intersection occur, by manipulating the actual window. Okay, and yes, from here you can still do analyze graph, look for the intersection to the left of this, scroll to the right, and it still pops up. So there is definitely manipulation of the window, the viewing window on the graphing calculator, okay, for this one. All right, let's go to method 4. We're going to look at now the table, okay? So we're going to use the same example. 4 to the power of 3x is equal to 6,000. But we're going to look at the table and see when does this occur, okay? So from here, I'm going to press Control-T to access the table. And then I'm going to start to see when will the x yield this 6,000 per se, okay? So let's come over here, and if you notice that all of these are already inputted as integers from negative like 3, and it just keeps going on and on and on, all the way to 0, and then it goes to the positive pieces. And what we're trying to see is, when does this equal this? When do these numbers match up, okay? So you see right here, 4,096, it's not equal to 6,000. We want them to be equal to 6,000, okay? Then it jumps way to 262,000. That's not equal to 6,000. So we know in between 2 and 3, that's when this function here, this 4 to the power of 3x will equal the 6,000. They will be equal somewhere in between 2 and 3. So what I have to do is I'm going to have to change my step size, okay? So let's come over here, and we're going to look at the table, and we're going to do Edit Table Settings, and let's change this to Ask. We want to input numbers and see how close we can get until it actually matches, okay? So we could say, we know it's between 2 and 3. So here's 2. At 2, we're at 4,096 and we're at 6,000. Not there, just not quite. At 3, again, these are those two numbers. We see that they're very, very far away. So we want to match them up and get closer and closer and closer. Now 2.5. Notice that we have 32,000 versus 6. Now we already know the answer. We know the answer is 2.09, but you see that there's a lot of guess and check here, okay? So if I say like 2.1, it gets closer and closer and closer to the answer. And you see 6,000 and 6208. They're getting closer and closer. Again, we already know the answer is 2.09. So you would play around with this and say 2.08. And you see now it's a little bit less than what the right side says is 6,000. So over here, it was too high. It was above 6,000. That's why 2.1 is too big. 2.08 is below 6,000. That's why it's too small. And that's why we're going to go in between somewhere and say 2.09. Okay? And you see, it gets closer and closer and closer to equal the same thing. Okay? What you can do here is you could do a lot of guess and checking for sure. Or you can even have the calculator just spit these out for you so that, check this out. You can have the table set, still have auto, but instead of jumping by one each jump, the way it did before, it had -3, -2, 0, or -1, 0, 1, 2, 3, those integer jumps. We could do it by smaller increments. We could say that let's jump by 0.01 every single time. So over here, you see that these are changing by 0.01 every single time. And if we were to scroll all the way down to the answer, you see this 34, the 6,000, and so on and so forth. These are getting closer and closer to some respect as we get closer and closer to the actual answer of 2.09. Okay, so 2.092 is the answer. And you see right here, 2.09, how close we get. Okay, so I went a little bit too much. But I wanted to show you both methods because as far as graphing and by the table is because it's not always the easiest way to find the answer. Okay, with the calculator, yes, we do have a feature that is on this particular calculator, but not on all calculators. Let me show you something real quick. If I did menu 3-1, a lot of you who know this feature, you're probably asking yourself, why didn't you just do this at the beginning? It's because this calculator is not allowed to be used on the ACT. And on the ACT, there are a lot of questions that are like this, or even the non-calculator questions on PSAT and SAT, like I said from before, that you will have to know how to do this by hand. This is why I didn't really want to show you this way, okay? Because chances are, and I mean high chances, I would say more than 90%, if you have questions like this, it's going to be without a calculator. You see, we get 2.092 very, very easily, much, much faster than the graph and by the table. That is why I'm stressing that we need to make sure that we are learning this with the same base and logarithms form, okay? Mostly the same base. I wanted to show you all that calculator stuff just now and how confusing it can get, because our goal is to learn this without a calculator as the same base method. Okay, so technically, yes, you could say there are 5 methods, and the 5th one is simply just doing the solve feature. But here's the thing. I will warn one more time. Try not to use this at all. If you're using it, it's only because you're confused and you're trying to check your answer. But to replace the learning, trust me, you do not want to do this solve feature. You want to actually learn it by the properties and laws of logs that we've learned.